Hello, my magnificent, fabulous, wonderful, fantastic children. We're going to continue on with section number 1 from your acids and base chapter. I just want to go through and review those properties of acids and bases. Also, on Thursday, we talked about Arrhenius, and then we also talked about Bronsted and Lowry. So let's go through and talk about them very quickly again. We'll finish up with Bronsted and Lowry. We'll start Lewis theory, and then Monday in class we'll finish up with Lewis and start into section number 2, okay? So 4 properties of acids. We know that they taste sour. We know that they can conduct electricity, and they can conduct electricity because they dissociate into ions once they're in water. And it doesn't just have to be water. It could be any solvent that will help them dissociate into ions. Water, again, is just that universal solvent that we always talk about. So for us, we just think about it in terms of water. Now, we know that electrolytes are substances that can conduct electricity because these compounds have dissociated into ions. And we have strong or weak electrolytes. Strong meaning that I have lots of ions that are able to carry around a lot of current. Weak electrolytes meaning that I still have ions that are dissociated in the water, it's just not as many, it's quite few. Another property of acids would be that they react with metals to produce hydrogen gas, that's correct. And in terms of color indicators, if we use litmus paper, then it's going to turn red. Now they also react with bases. And when they react with bases, they will form 2 products. And what are those 2 products? Water and salt. And that happens in what type of reaction? What's the name of that reaction called? Neutralization. Now, in a neutralization reaction, since we're reacting an acid and a base to get water and salt, then the base has to be some type of hydroxide. So Arrhenius's model is the best one in terms of thinking about neutralization reactions. We know that acids also have a pH of less than 7, and acids usually start with hydrogen. Now, in terms of bases, we know that bases can react with acids to have a neutralization reaction. They taste bitter, they feel slippery. They also are considered to be electrolytes because they can dissociate in water to create ions and carry a charge. So we have strong electrolytes there and also weak. And when they change litmus paper, they won't change it red, they're going to change it blue. Now, we also know that bases have a pH of greater than 7. And we said that in section 2 is where we're really going to get to that concept of pH. And I think that you did that on Friday whenever you did your POGL on calculating pH. So also talking about your POGL, I would like you to bring that packet with you that you did on Friday back to class on Monday, because that will help us get into section 2. And I'd really like to hear what questions you had about that from Friday. So getting into the acid-base theories, on Thursday we talked about Arrhenius, and we know that he was one of the first chemists to introduce the concept of acids and bases. And his model stated that acids are substances that can produce hydrogen ions. And we know that his base was a substance that can produce hydroxide ions. So we talked about before that his model is very limited because bases have to contain hydroxide ions. And we have some bases that don't have hydroxide in them. So that model isn't general enough to define all bases. One of those bases that he couldn't define was ammonia, NH3. And we talked about how Bronsted and Lowry on Thursday could define that as a base. So Bronsted and Lowry came along, they took Arrhenius's model, and they generalized it, they broadened it. And so they defined an acid as a hydrogen ion donor. It's something that will give away a hydrogen in a reaction. And then they defined a base as a hydrogen ion acceptor. It's something that's going to take in that hydrogen ion. So I have a fantastic group video project that came up with BAR, bases accept and acids release. So if you forget, remember Bronsted-Lowry is just bar, bases accept, acids release. It's fantastic. And Bronsted and Lowry found that acids and bases will always come in pairs, and they called these conjugate pairs. So it's really important that we know that they are calling these conjugate pairs, okay? In terms of why ammonia is a base, we talked about that on Thursday. Let's go to their idea, Bronsted and Lowry's idea of conjugate acids and bases, or conjugate pairs. So we know that in a acid-base reaction that the reactants are, one's going to be an acid, one's going to be a base. Well, the products that I produce are the conjugate pairs. So in the products, one's going to be the conjugate acid and one's going to be the conjugate base. According to Bronsted and Lowry, so this is on slide 26 if you're following along with your PowerPoint slides. According to Bronsted and Lowry, a conjugate base is a species that's produced when an acid donates a hydrogen. Okay, so it's the remainder of the original acid, if we're thinking about it that way. And then a conjugate acid is the species produced when a base will accept a hydrogen. So down below, I gave you an example. We have hydrofluoric acid plus water is going to react to produce hydronium ion and then the fluoride ion. So I wrote that out also here for you. Oh, wrong one. That's the reverse. Okay, so I have hydrofluoric acid, and then I have water that's going to produce hydronium ion and then the fluoride ion. So I know that hydrofluoric acid is the acid, not only because it has acid in its name, but because if I look over on this side, HF is donating or losing a hydrogen. So this has to be my acid, according to Bronsted and Lowry. H2O, water, has to be the one that's acting like the base, because over here on the product side, it gained an extra hydrogen. So we call the species that accepts that extra hydrogen, we call that the conjugate acid. And then the species that's produced when the acid donates that hydrogen, so what's left without the hydrogen, we call that the conjugate base. So I have my acid, my base, my conjugate acid, my conjugate base. Now if we flipped this reaction and looked at it the other way, because these are reversible. Remember, we know that the arrows just mean that they're reversible reactions. Let's say that we start off with hydronium ion and we're going to react that with fluoride ion. As my products, I'm going to get water and hydrofluoric acid. So in this situation, I have my hydronium ion acting like an acid. Why? Because it's donating a hydrogen. It's losing that hydrogen to become water. And my base is going to be the fluoride ion because it's accepting on the product side over here a hydrogen ion. So in this case I have hydronium, again, as my acid, fluoride ion as my base. If we go back and look at the products from the other ones, hydronium ion was a conjugate acid, so it should act like an acid in the flip reaction. Fluoride ion was the conjugate base that was produced, so if I flip that reaction, it should act like the base in the reverse reaction, and that's exactly what they do. So this is what Bronsted and Lowry called conjugate pairs, because when you flipped them, the conjugate acid would be the acid in the reverse reaction, and the conjugate base would be the base in the reverse reaction. So let's move on. If you go to slide number 27, I just wrote out a general equation for you. So we have HA plus H2O will make hydronium ion plus A minus. So this is just a general acid plus, let's just say that water can be acting like a base in this case, will make the conjugate acid and the conjugate base. So in the acid-base reactions, I will always have on the product, or on the reactant side, an acid and a base, and then on the product side, I'm always going to make a conjugate acid and a conjugate base, okay? Now I gave you two different reactions as an example here. We have NH3 plus H2O will make ammonium and hydroxide, and then I have HCl plus H2O is going to make hydronium and then chloride. So in these reactions, I know that on NH3, that's acting like a base, so then water must be acting like an acid on that first reaction. On the second reaction, HCl is my acid, and now water is acting like the base. So this is to show you that water, in both of these cases, it's first acting like an acid in the first reaction, and in the second reaction, it's acting like a base. So a substance that can act as an acid or as a base, we call those substances amphoteric. So they can show or exhibit properties of an acid, or sometimes they can show or exhibit properties like a base. Now, on the next slide, slide number 28, there's a learning check. And this is just to identify the conjugate acid-base pairs in each reaction. You'll see that there are 3 reactions that I wrote out for you in chemical formulas, and then there's one that I just gave you the reactants. No, I take that back. I gave you the products, and I want you to write the reactants, the products, the entire reaction out, and then I want you to identify acid-base, conjugate acid-base, and or conjugate acid-base pairs. So I would like you, for your homework for this weekend, to do all 4 of these questions on this learning check. So tell me, what's the acid, what's the base, what's the conjugate acid, and what's the conjugate base. So just write out the reactions and then label them for me, okay? Now, if we move on to slide 29, this is talking about monoprotic acids versus polyprotic acids. So if we think about mono versus poly, mono just means one, and poly means many. So the first ones that I have listed here for you are HCl and HF. And if I add HCl to water, I know it's going to dissociate into its ions. So that's going to break apart into H plus and Cl minus. Now this Cl minus doesn't have any extra H's added to it. So this is considered a monoprotic acid because HCl can only donate 1 hydrogen. It can only give away 1 hydrogen ion. The same thing for hydrofluoric acid. When I add hydrofluoric acid to water, I'm going to get H plus and then F minus. I'm going to get hydrogen ion and fluoride ion. Since this only has 1 hydrogen, it's monoprotic because that means it can only give away 1 hydrogen ion. Now, in terms of polyprotic, we could have, let's do H2SO4. So H2SO4 we know is an acid, and when I add that to water, it will break down into H plus HSO4 minus. So I get these 2 ions. Now this HSO4 minus could donate another hydrogen. So I can donate 1 here, but it could on this side after I've produced this, after it's broken down, this one could give away another hydrogen. So that can break down to H plus and my sulfate ion. So we would call this a polyprotic acid because it could, H2SO4, sulfuric acid, could donate up to 2 hydrogen ions. So that's why it would be considered a polyprotic acid. So really the way that you can, figure this out is to determine how many hydrogens that you have that we would call ionizable. And this is the next part on this slide. An ionizable hydrogen atom. Ionizable atom just means that it's bonded to a very electronegative atom. So I can get these partial charges. It's easier for water to come and attract a hydrogen that's ionizable, meaning that it's already got a bond with something in terms of partial charges. So an acid must have an ionizable hydrogen or otherwise it's not going to donate. If you go to slide number 30, the next slide, a few organic acids can show us the difference here. So acidic acid is CH3COOH, or we also know that as C2H3O2 with that little -1 charge, right? That's acetate. If we add that hydrogen there, it just gives me HC2H3O2. Okay? So same thing, we just wrote it in a different way. So that way we could see which hydrogen was ionizable. So for acidic acid, CH3COOH, I gave you a diagram of what that looks like. So I have oxygen bonded to hydrogen here. And I know that oxygen is very electronegative, and I know that it's attached to that hydrogen, so I'm going to get a nice dipole there. I have a partial negative charge on the oxygen, a partial positive charge on the hydrogen. Because of that, then that hydrogen can easily be donated, that base can come in and attract it, and then that hydrogen will come off of that acidic acid. Now, the CH3, those other three hydrogens are not ionizable because carbon and hydrogen don't have a very strong electronegative difference between them. They actually have a nonpolar bond. And since they have that nonpolar bond, I can't deal with charges, so when they go into water, they're not going to dissociate, or I can't have that water molecule pull away those hydrogen ions because polar doesn't dissolve the nonpolar compounds, which we talked about in the previous chapter. So if you look at the picture to the right with the ring that has the carbons and then the hydrogens around it, that's called a benzene ring. And this is just another organic compound. And all of these hydrogens on benzene are considered not ionizable because there are no partial charges where those hydrogens could be released to be given to the base, or so that the base could attract them, okay? Now, we said something a little bit before about polyprotic acids, moving on to slide 31. Some compounds have more than one ionizable hydrogen to release. So hydrochloric acid, hydrofluoric acid only have one hydrogen, so those are called monoprotic acids. Or same thing here, like nitric acid, HNO3. It only has one hydrogen to give away. Sulfuric acid has two hydrogens to give away, so it would be diprotic, so it would be considered a polyprotic acid. Phosphoric acid, H3PO4, is a triprotic acid because it has three hydrogen ions that it could give away. Now, one thing that I want to add here is that having more than one ionizable hydrogen does not mean that it's stronger. Just means that it has more hydrogen to give away. So just because I'm giving away more hydrogen doesn't have anything to do with strength, okay? And let's say that, let's save the next slide, slide 32, for the steps of polyprotic acids. Let's save that for class on Monday because I'd like to walk through those together. And then let's just do this last slide here, slide 33, and introduce Lewis acids and bases, at least just the definition of them. So Lewis was our last and third theory of acids and bases. And just like Arrhenius focused on acids being hydrogen ion producers and bases being hydroxide ion producers, then Bronsted and Lowry focused on an acid as donating a hydrogen and a base accepting that hydrogen. Lewis wanted to make it even more general by not even using hydrogen at all, but thinking about acids and bases in terms of electron pairs. Now, we have talked about Lewis before when we talked about his Lewis dot structures. So for him, acids and bases made sense because he always thought about how electrons are transferring or traveling between compounds. For him, a Lewis acid was defined as an ion or a molecule with a lone vacant atomic orbital that could accept an electron pair. So an acid is something that will accept an electron pair. And a Lewis base is going to be a compound or a substance that can donate an electron pair. So an acid is an electron pair acceptor, and a base is an electron pair donor. And then the next slide is blank because I want to go through on Monday several examples of electron pair donors and acceptors. So that way you can see that movement of those electron pairs between acids and bases. So we're going to stop here. And don't forget that that learning check on slide 28 is your homework, and that will be due at the beginning of class on Monday. If you have any questions, post on the blog, and I will see you guys on Monday. Have a great weekend. Bye.